Let's see. Hello, everybody. I am Sabrina, and today I'm going to be giving you a little glimpse of just what I based my portfolio around. So a little bit about me. I actually did not come into Berry with a creative technologies major. I actually came in as a history major because I wanted to avoid doing STEM as much as possible. I had a pretty bad experience doing coding in high school, and I really disliked it. But my first semester here at Lee, powers that be actually placed me in an intro to creative technologies class. And so I got a little taste of what it was like being at the lab and making things. And I mean, you can figure out where we ended up after all that. In terms of personally, I'm a huge fan of 3D printing. This actually started 3 years ago when we were told not to come back for spring break because of the pandemic. I panic bought an Ender 3 to work on my Creative Tech 101 projects. And that ended up being a little bit more of a roller coaster than I was anticipating. I spent probably 6 months trying to fix the thing. And eventually, after sort of getting frustrated with it and then fixing all these problems that were coming up with it, I realized 3D printing's pretty cool when it works. And so I found a lot of satisfaction in finding these issues that were happening with the 3D printer, improving it, and then using it to get these tangible products out of it. And so I'm just kind of chasing that now, and it's been downhill since then. I'm also a huge fan of drawing. So for every single one of my projects, I produced sketches of them prior to modeling them out using like a 3D modeling software. And so I think that contributes a little bit partially to like my favoritism towards 3D modeling a bit. Just because it's so tangible, you can see what you're doing. It feels a lot like using your hands to make something, except it's all software based. So in terms of what my theme is, it is utilizing 3D printing and design to develop geometry-inspired solutions. And so what y'all can expect to see during this portfolio review is you can expect to see a lot of 3D modeling using Fusion 360. You can expect to see a lot of 3D printing. And really those are the big two, a lot of CAD and a lot of 3D printing. So those are really my two favorite things. And I try to do as much as I can with them just to make my skills better with that sort of field. And so going in chronological order here, this was actually my first huge foray into 3D modeling. So prior to taking Chris's Fusion 360 class, I'd only ever used Tinkercad. And so while I was learning how to use Fusion in Chris's class, I wanted to really push myself to display everything that I had learned over the course of that class in using sculpting, using all kinds of circular patterns, and just all of these tools in Fusion 360 to make something that personally means a lot to me, but also sort of displays what I have learned over that time period. And so this here was actually my first huge Fusion 360 project. This is the Fusion Mustang. It was a recreation of a P-51D Mustang built with Fusion 360, complete with moving parts. And so one of the big parts of this actually is I sculpted it alongside several canvases that I had calibrated to fit a real P-51's dimensions. And so, let's see, where's the little laser? So you can kind of see up here, the yellow is my model. You can kind of see a little bit, this is my propeller, and this is the propeller on the canvas right here. And so I imported these pictures essentially of real P-51 Mustangs into Fusion, calibrated them out to the actual length of a real Mustang, and then used Fusion's form tools to actually sculpt a body alongside that. And so here you can see I used this model for the wing profile. I believe this is actually a toy Mustang. This is the best I could find of the top view. But here you can see I very closely followed how the wings would look there, and just trying to match it as closely as possible to several different reference images. It was a very fun challenge, honestly. I found working alongside these reference images was very satisfying, and then seeing when it fits so well after, it just filled me with kind of joy. And so after sort of sculpting it, I created these moving joints that sort of give it a little bit more realism. So these are the parts that you could expect to move on a real airplane. I created a motion link between these two bits of landing gear and then this rear wheel back here. So whenever these move up, this moves up. And that took quite a while to figure out. I constrained it as best I could to the dimensions I was given and to the reference images. And so this is the finished product. Here you can also see that the flaps back here move along with this cockpit. because Jiffy is a wonderful, wonderful software. It only allows me to use 6 seconds of footage. And so wherever you see one of these little flags here or something similar, these are all moving parts. And so both of these flaps back here move, the tail moves, the little landing doors that cover landing gear back here moves, and all of these flaps also move. And so this really helped me develop my skills in Fusion 360 and using joints, because prior to that point I had very little experience using these sort of joints in Fusion. And so this really gave me a great sort of crash course on using those and then constraining them and making them look realistic. And so this is still one of my favorite Fusion projects to date, and it's really sort of kicked off my love of 3D modeling. And so next here, this one actually has an interesting little bit of story behind it. So I have a lot of plants at my house, a lot of plants, and they're all constrained to this one table. And so whenever it is wintertime, because a lot of these plants are tropicals, I have to bring them inside as soon as it dips below 50 degrees. And this clutters up my plant table just to an obscene degree. And so I wanted to create a way that I could declutter this table using 3D modeling and 3D printing. And so I eventually developed this stacking planter. So the stacking planter is a set of interlocking 3D printed plant pots that you could stack on top of each other. You could lock them together, and you could also use them as storage for unused pots and then eventually bring those out. And so what you don't see here, there are actually 2 pots under this bit of rainbow pots here. So I wanted to create something that would take your eyes away from the clutter and bring it towards what you wanted people to see. And so this took a lot of tooling in Fusion 360 in developing these tolerances. There was a point where in Chris's class, I had made these 2 pots so tightly interlocked that Chris, when he was trying to pull them apart, they flew across the room. And so it took a lot of trial and error. And so here you can kind of see the geometries of the interlocking solution. It was a little difficult trying to figure out just what the printer could do and what the printer was capable of, so that impacted how deep I made these features. But if you look very closely over here, this phantom pot fits perfectly into this impression here, which is the same impression here. Looking back at this pot, it actually had a tolerance of 0.1 inches. And so this allowed it to lock together, but not stay so locked that you couldn't get them apart. And this really was taking the Fusion 360 that I had learned in just modeling and also bringing it into the real world. So this was a tangible, physical, usable object. And so while the Fusion Mustang was a lot of fun to work on, it wasn't meant to be 3D printed immediately. And so this was, I think, the first practical 3D print I had created up at this point. And here, this actually was not done as part of the class. This was done as part of some faculty-led research here on campus with Dr. Joe Cochran. When learning math in high school, there's a lot of talk about formulas and equations, and it can be difficult for people who are very visual, like myself, to sort of grasp these mathematical concepts. And so the issue that this research and this website was seeking to remedy was people lacking the understanding of math because of a lack of manipulatives. And so the objective of this website was to create mathematics and 3D printing curriculum to sort of help students grades K through 12 to better understand mathematical concepts. And so every single lesson on this website has something to do with 3D modeling or 3D printing. And so you can kind of see here, this was, I believe, grades 6 through 8. You can see some of the lessons, like cross sections. This actually went on very strongly to influence some of the work I did down the line after this. But this website actually shows teachers not only how to use 3D printing to change their curriculum and make it more exciting for students, but also how to use 3D printers themselves and how everything works, so that way they have a better, more solid understanding of what is going on there. And so this was actually based on research that was done prior to this website being made, that essentially the basis of this research is that students have a better time 3D modeling when they haven't drawn it beforehand. So when they try to draw and visualize these objects prior to 3D modeling, they actually did a worse job at it. And so essentially that is what built or formed the cornerstone of this website here. And so I did a lot of the work for the HTML on this website. So this cube actually was made in Tinkercad as part of a lesson, 3D printed, and then I actually took this picture at my house on a table. Um, and so a lot of the work that I ended up doing with this project, I did a lot of the 3D printing of these solids. I did photography of these solids to better visualize what these teachers should be looking for, what they should be doing. I actually did a lot of the brushing up in HTML. So it kind of gave me a leg up in some of the classes down the line that involved a lot of web development. I had some of that front end experience already. And so I was going in, editing the stuff that was written, adding pictures in, adding in videos, filming videos, and just doing a breadth of things to make the user experience of this website a lot more satisfying, a lot more interesting to teachers. And so here you can actually see we presented our research recently. Actually, back in January, we went to a STEM conference up in Tennessee at, I believe it was Tennessee Tech University. And so we were presenting the basis of the research, which is the students having a better time 3D modeling when they hadn't drawn. But we also had a little segment here for the website, and people were actually able to visit it and see just what we were talking about, which was a lot of fun. A lot of people displayed some very tangible interest in this. And so it felt really good to me to know that the work that I had done on the website was actually going and being useful to these people. And so following the sort of math geometry theme, we come to my capstone, which is Platonics. And so Platonics, sort of explain a little bit about the name. PLA is a material that you 3D print with, and so these are platonic solids, Platonics. And so, yeah, I patted myself on the back for that one still. Yeah, and so the issue that these were essentially trying to solve is people had a hard time understanding cross sections of platonic solids. So there was an interesting story behind this where while I was working as a research assistant with Dr. Cochran, she was talking to us about her geometry class and how she gave them worksheets that told them identify the platonic solid based on 3 cross sections from it. I couldn't figure out any of them, and so this spurred a very interesting conversation about how can we make these cross sections easier for these people to visualize, not only like college students but also like high schoolers, because it can be a little tough mentally trying to see a cube and then slicing it at an angle to where you see a triangle. So this was meant to sort of help those visual people figure out just what cross sections were on a platonic solid. And so each of these was 3D printed and designed in Fusion 360. And so they're actually on that little table right there. Feel free to interact with them. It's kind of what they're meant to do. And so the goal really was to help these high school students understand cross sections a lot better. What I ended up doing, I did a lot of consulting with Dr. Cochran outside of sort of busy hours about what cross sections I should be implementing and how the solids felt, and just making sure the usability was top notch. And so in order to sort of maximize this usability, I set 3 design goals for myself, and that would be that they would be easy to 3D print even for the absolute beginner. They would display cross sections from multiple angles, and that they would be easy to use. Because if you had something that displayed cross sections but was incredibly hard to use, you wouldn't want to really interact with it at all. And so the whole easy to 3D print bit really contributed a lot to the design of these solids. And so here, actually, this is the first chronological solid that I started with. This is the tetrahedron. And so here you can actually see the hinges in this object are completely integrated. They are not sticking out, they are completely internal. And so the goal here was to make this as easy to 3D print as possible by just laying it flat on this face on the build plate, no supports, no assembly, no nothing, and having it 3D print like that. And so this actually was not my original goal when I was designing hinges. I was initially thinking I could design a hinge, import it into Fusion 360, and then 3D print it from there. And I was a little disappointed. There was a lot more to it than that. And so after a lot of sort of research and development of how these hinges could work better, I ended up settling on this design, but I didn't end up sticking with it because it ended up bringing challenges of its own. And so here we have the second set of solids. These are octahedrons. And so the reason there are 2 solids here instead of just one, like the tetrahedron, the octahedron actually has a really neat hexagonal cross section that you don't normally find. And so I wanted to include this, but at the time I believed that this particular octahedron right here, the blue one, did not have enough room for a hexagonal cross-section or the hinges that came along with it. And so I ended up developing two sets of cross-sections. And so this yellow one here displays the hexagon, and it also displays a square. So that way, theoretically, they could stand by themselves. It would just be up to the teacher to choose whichever cross-section they want to present on. This one did bring a lot of challenges of its own, especially with the angle at which hinges 3D printed. One of the issues with these internal hinges is that you couldn't always lay them all flat on the build plate. And so I had to take into account the angle at which they were being 3D printed, the sort of angle at which I needed to lay these things on the build plate to sort of minimize them breaking apart during the 3D printing process. And so this actually led me to sort of pivot my design quite a bit and move to external hinges. And so here, this was actually my first foray into external hinges. At the time, I was a little hesitant to sort of go into this just because I'd spent so much time developing the internal hinges. However, these actually remedied what I believe was a sort of fragility with these previous two solids, because people have been, my committee members have been telling me, these feel fragile, I feel like they're going to break in your hands. And that had happened during the 3D printing process. I'm like, absolutely, I totally believe you. And so I ended up working off of sort of reference images of a door hinge to develop these up here. But this also led me to another problem. How could I 3D print these without supports if they're just hanging out in midair? And so this led me to sort of making these very specialized hinges at a sort of 40-degree angle. So that way, slowly but surely, the 3D printer just build them up layer by layer without any sort of messy, drastic overhangs that would result in any sort of issues while 3D printing. And so that sort of leads into the ease of 3D printing, even for the absolute beginner. None of these require supports at all. The supports that I did include here, these are actually just little profiles that I extruded that just kind of keep these angles from printing in midair. You can snap them off with your finger after it's done 3D printing, so there's really no post-processing after this. And so from here, I carried this design into the icosahedron. And so we have another 3 cross sections here, made completely the external hinges. So this one I actually found was probably easier to 3D print than the hexahedron. It didn't require any little pin supports at all, just because the face that it's laying on here, actually it was the face that was laying on here, ended up working perfectly for 3D printing. And so very pleasantly surprised by that. However, down the line, I would end up finding that this cross section right here would cause some issues for understandability. And so this would end up sort of rearing its head a little bit. And here we have the most recent and final platonic solid. This is a dodecahedron. This was actually developed after I had spoken with some teachers, which I'll get to in a little minute. This was developed after I gathered feedback from some outside of Hackberry people that said these things need to be changed just because it's not good as is, it feels too fragile and things like that. And so I ended up downsizing from 3 cross sections on the previous 2 solids to 2, just to make it a little simpler and a little easier to 3D print. And so this one, I ended up adding some more supports that were also pretty easy to remove. Along this side right here, I put in some little pegs that you can just snip with a pair of wire cutters that come with the 3D printer, and then it opens right up. So very happy with how this final one came out. However, this sort of brings me into my next little point here. I actually spoke with some geometry teachers from Rome High School about these, just to sort of get that human aspect in it, because you can develop something that you think is really great, but you don't have the experience teaching it. So what technically do you know about how to make it for this particular audience? And so Dr. Cochran actually helped me reach out to 4 high school geometry teachers at Rome High. We met, I showed them all of my platonic solids up until the dodecahedron, because I'm still 3D printing that one. And so I ended up using their feedback to try and improve the final model a little bit. And so some of their specific points that they made was that they felt the models were too complicated. And so with the 3 cross sections, these models were a little hard to show people, a little hard to use. And so there's this interesting point that actually came up where teachers don't want to be seen struggling with something in front of the class. And so trying to find the cross sections of the hexahedron, for instance, was sort of like trying to solve the Rubik's Cube in a few seconds while being judged by an audience of high schoolers, which are notoriously harsh critics. And so I ended up scaling down the dodecahedron for that reason. And the icosahedron, which what I talked about a little bit earlier, some of the limitations on that particular cross section had a bit that was not cut particularly well. And so one of the teachers actually correctly pointed out this interferes with how it's presented. And so this led them to saying, we would like simpler cross sections made available that only have one cross section each, one model, one cross section. So that way it's easy to open up and show people. Maybe it's not necessarily as fragile or has as much play to it as the more complicated models, and is able to display these cross sections accurately. Because at one point, one of them actually said, with the hexahedron, it's great that it has these colors and these cross sections, but you can't really see how it's sliced to get to each one of these. And so I thought that was a fantastic point. So that's where I sort of carried it into the dodecahedron and its design goals. And so in terms of what's next, down the line, I would like to make Platonics better. I would like to continue working on this for sure. I actually have my mini factory and Thingiverse pages up for these. I've been applying to a lot of jobs recently that sort of involve the 3D printing and Fusion 360 CAD realm, just sort of finding ways to make prototypes, 3D print them, improve upon them. I found that the iteration process that I followed for Platonics was a lot of fun, actually, despite its frustrations that it came with. And so I really would like to find jobs sort of related to this. And in between sort of bringing Platonics to the internet and improving it and making simpler models available, I'm trying to teach myself AutoCAD because that seems a little bit like the industry standard nowadays alongside SolidWorks. And I would eventually like to end up in a 3D printing related role, but I'm going to be interning at WireTech until I find something better. That's sort of my plans for the future. Do you have any questions?